Solving Linear Diophantine Equations by Professor Frey. Linear Diophantine equations. When we require that all solutions to a particular equation come from the set of integers, this equation is called a Diophantine equation. The equation ax plus by equals c, where a, b, and c are integers, is a linear Diophantine equation in two variables. We are interested in exploring when these equations have integer solutions and in solving these linear Diophantine equations. So theorem. Let a and b be integers with the greatest common divisor of d. The equation ax plus by equals c has no integral solutions if d is not a divisor of c. If d does divide c, then there are infinitely many integral solutions to this linear Diophantine equations. Moreover, if x equals x naught and y equals y naught is a particular solution of this equation, then all of the solutions to this equation are given by the equations there. So we need to find one particular solution, and then we can use these formulas to find all of the rest of the solutions. Linear Diophantine equations demonstration. Here's a demonstration of what this looks like graphically. Okay, we're going to take a look at this site from the Wolfram's demonstration project. Here we see the graph of negative 10x minus 10y equals negative 40. So all the points on this line represent solutions to that equation, and the red dots represent solutions to the linear Diophantine equation. In other words, integer solutions to that linear Diophantine equation. And notice the greatest common divisor between negative 10 and negative 10 is 10. That divides evenly into 40. So we did expect solutions. In fact, we expect infinitely many solutions. And if we zoom out on this graph, the further we go, the more solutions we're going to see. Now we're looking at the graph of negative 7x minus 10y equals negative 40. Here the greatest common divisor between negative 7 and negative 10 is 1, and again that divides evenly into negative 40. So we expect to find solutions to the linear Diophantine equation. In fact, we've got one here, and it looks like another there, and if we zoom further out, we're going to see more and more of those solutions. Here's an example of a linear Diophantine equation with no solutions. We've got negative 9x minus 6y equals negative 40. Greatest common divisor between negative 6 and negative 9 is 3, and 3 does not divide evenly into negative 40. So by the theorem, we do not expect any integer solutions to this linear Diophantine equation. And in fact, the farther we zoom out, we're not going to see solutions. Okay, so that gives you an idea about how this works graphically. The next thing we're going to want to do is to be able to find all of those integer solutions to the linear Diophantine equations. We need to thank the Wolfram's demonstration project for those graphs, and particularly Emmanuel Garcia's Medina, who contributed the linear Diophantine equations demonstration to the Wolfram project. So thank you both. So now let's see how we solve one of these linear Diophantine equations. The first part is to use the Euclidean algorithm to find the greatest common divisor, and then use some back substitution to express that GCD as a linear combination of the two numbers. So let's see how that works. What I want to do is take the two numbers, 87, take the larger of the number, 87, divide it by the smaller of 27, and it's 3 times 27 plus a remainder of 6. And then I'm going to repeat that process on these two values. So 27 is 4 times 6 plus a remainder of 3. And again, I repeat and continue until you get a remainder of 0, which is going to happen now. 6 is 2 times 3 plus 0. So the last non-zero remainder we got. 3 is the greatest common divisor of the two numbers. So 3 is the greatest common divisor of 87 and 27. Next, we want to express the GCD as a linear combination of the two numbers. Okay? The first thing we want to do with each of these equations with non-zero remainders, we're going to solve for the remainder. So 3 is equal to 27 minus 4 times 6, and 6 is equal to 87 minus 3 times 27. Okay? I'm solving for the remainder and swapping sides, that's all. The last step, we're going to take this equation, the last equation here, rewrite it. 3 is equal to 27 minus 4 times 6. Now this equation tells me that 6 is equal to this value. That's a new name for 6. What I want to do is take this 6 out and replace it with that new name for 6. So I've got 3 equals 27 minus 4 times new name for 6 is 87 minus 3 times 27. Now here's the tricky part. I want to use the distributive property and then combine like terms. What I want to combine is this 27 and the 27s I've got here. So I've got 127, and then I've got negative 4 times negative 3, which is positive 12 times 27. 127 plus 12 gives me 13 times 27 minus 4 times 87. And you can multiply 13 by 27 and subtract 4 times 87 and just verify that that is in fact 3. You can catch your own arithmetic mistakes that way. So now I wanted to express that GCD, 3, as a linear combination of 87 and 27. So I'm just going to rewrite this equation as 27 times 13 plus 87, right? Because my two numbers were 27 and 87. 87 times negative 4 equals 3. Right? I've just rewritten this equation. Okay, so now let's take a look at part B. We're going to use our work in part A, so I've got to leave that up there. To solve the linear Diophantine equation 27x plus 87y equals 15. Well, I've got 27 times a number plus 87 times some other number equals 3. I'd like it to be 15. This is where we need the greatest common divisor, d, to divide evenly into this constant. So I can just multiply by 5 on both sides and get 15, and I'm going to do that carefully. So I want 27, and I'm going to multiply the 13 by the 5, so my coefficient stays the same. So 27 times 65 plus 87 times negative 4 times 5 is negative 20 equals 15. Right? So I've multiplied this 13 by 5, the negative 4 by 5, and the 3 by 5. Okay. Well, if we read this equation, we wanted 27 times some number plus 87 times some other number equals 15. Well, I've got 27 times a number plus 87 times some other number equals 15. I found a solution. And that solution is x naught equals 65 and y naught equals negative 20. So we can use that particular solution plus the formulas we have for all solutions to find the rest. So we got x equals x naught plus b over d times n, and y equals y naught minus a over d times n. Plugging the appropriate values into those formulas, we get x equals 65 plus b, which is 87, over d, which is 3. So 87 divided by 3, 29n. And y equals y naught, negative 20, minus a, which is 27, over d, which is 3. So 27 over 3 is 9n. So these formulas give us all solutions where n is any integer. In particular, if n equals 0, you get the x naught, y naught values we already saw, and you can plug in n equals 1, 2, 3, or negative values as well, etc., to find more solutions to the linear Diophantine equation. Now let's try this with a problem that's a little bit longer. First, we're going to express the GCD of 155 and 102 as a linear combination of the two numbers. So first, the Euclidean algorithm to find the greatest common divisor, again, we repeatedly use the division algorithm. So we know that 155 is 1 times 102 plus a remainder of 53. And then 102 is 1 times 53 plus a remainder of 49. And 53 now is equal to 1 times 49 plus a remainder of 4. 49 then is 12 times 4 plus a remainder of 1. And finally, 4 is equal to 4 times 1 plus a remainder of 0. So the greatest common divisor is 1. Next, solve each one of these equations for the remainder. So 1 is equal to 49 minus 12 times 4. 4 is equal to 53 minus 1 times 49. 49 is equal to 102 minus 1 times 53. And 53 is equal to 155 minus 1 times 102. The process is going to be exactly the same. We're just going to have a few more steps here. So again, we're going to start with the bottom equation. 1 equals 49 minus 12 times 4. And then we're going to move up to this next equation here. And we want to replace this 4 with new name for 4. So 1 equals 49 minus 12 times, in parentheses, 53 minus 1 times 49, close parentheses. We're going to combine the 49s. We've got one of them plus 12 more, because it's negative 12 times negative 1. So we've got 13 times 49 minus 12 times 53. Okay, and then we're going to use this equation and replace 49 with this expression. So 1 equals 13 times, new name for 49, is 102 minus 1 times 53. And then we've got minus the 12 times 53. Okay, we've got 53 here and 53 here. Those are the terms we want to combine. So we've got 1 equals 13 times 102. And then we're going to have minus 13 times 53, minus 12 more, so minus 25 times 53. So we need to go through this process one more time. We've got 53 equaling 155 minus 1 times 102. So let me put that right over here. So we're going to replace this 53 with new name for 53. 1 equals 13 times 102 minus 25 times 155 minus 1 times 102. Hopefully this is all going to fit. Okay, so we've got 102 here and 102 here. We're going to combine those terms. We've got 13 of them minus a negative 25. So 38 times 102 minus 25 times 155. Okay, so we wanted to express the greatest common divisor as a linear combination of 155 and 102. Let me rewrite this. 155 times negative 25 plus 102 times 38 equals 1. And we've completed part A. Now, using that information, we want to solve the linear Diophantine equation 155x plus 102y equals 6. So we've got 155 times a number plus 102 times a number equals 1. And we'd like 6 here. We want the right-hand side to be 6. So what we're going to do is multiply through by 6. So we got 155 times negative 25 times 6, which is going to give us negative 150, plus 102 times 38 times 6, which is going to give us 228, equals 6. Okay, so we've found a particular solution. X naught equals negative 150, y naught equals 228. That's one solution to the equation. And then the rest of them we can find by using the formulas again. X equals x naught, negative 150, plus b over d, so that's 102, over the greatest common divisor of 1, so just 102n. And y is y naught, which is 228, minus a over d, so that's 155 over 1, or 155n. So there is the formula for all solutions to that linear Diophantine equation, where n, again, is any integer. I'm going to go through one more example here, and I'm going to go through it a little more quickly. I encourage you to pause the video and try to do the parts before you see me work through. The first part we're going to do is to find the greatest common divisor of 87 and 103 using the Euclidean algorithm. So 187 is 1 times 103 plus a remainder of 84. 103 is 1 times 84 plus a remainder of 19. 84 is 4 times 19 plus a remainder of 8. 19 is 2 times 8 plus a remainder of 3. 8 is 2 times 3 plus a remainder of 2. 3 is 1 times 2 plus a remainder of 1. And 2 finally is 2 times 1 plus a remainder of 0. So the greatest common divisor is 1. The next step is just solving for all of the remainders, so I'll start at the top this time. 84 is 187 minus 1 times 103. 19 is 103 minus 1 times 84. 8 is 84 minus 4 times 19. 3 is equal to 19 minus 2 times 8. 2 is 8 minus 2 times 3. 1 is 3 minus 1 times 2. Now we're going to work on the back substitution. So we're going to start with this equation. 1 equals 3 minus 1 times 2. And then we're going to replace 2 with this expression. 1 equals 3 minus 1 times, new name for 2 is 8 minus 2 times 3. Okay, and we want to combine the 3's. So we get 1 equals 3 plus 2 more, so that's 3 times 3 minus 1 times 8. And again, you can verify 3 times 3 is 9, minus 8 is 1. Okay. So we finished with that. The next thing we want to do is replace 3 with this expression. So 1 equals 3 times 19 minus 2 times 8, in parentheses, and then we have the minus 1 times 8. We're going to combine like terms, so we've got 8's. We've got 3 times negative 2, so negative 6 of them minus 1 more. We've got negative 7 times 8 plus 3 times 19, because I could have put the 19's first, but it doesn't matter. Now we've got 8, and we want to replace it with this expression. 1 equals negative 7 times 84 minus 4 times 19. And then we've got 3 times 19 from above. Okay, again, we're going to combine the 19's. So I've got negative 7 times 84. I've got negative 7 times negative 4, so that's 28 times 19. Got 28 plus 3 more is 31 times 19. 2 more to go. We got 19. We're going to replace it with that expression there. So I got 1 equals negative 7 times 84 plus 31 times, new name for 19 is 103 minus 1 times 84. Okay. So we've got 84 and 84. We're going to combine those terms. We've got negative 7 of them minus 31 more. So negative 7 minus 31 is negative 38 times 84 plus 31 times 103. And lastly, the 84 gets replaced with this expression, negative 38 times 187 minus 1 times 103, and then plus the 31 times 103 from above. And I'm going to combine like terms. So I've got some 103s here and some 103s here. I've got negative 38 times negative 1, that's 38, positive 38 times 103, plus 31 more. So 38 plus 31 is 69 times 103. And then we've got minus 38 times 187. And we've completed part A. So now we're going to use our work in part A to solve the linear Diophantine equation 187x plus 103y equals 5. And I've just copied our final answer from part A down. Now we want to rewrite this in the form of the equation we're given. So we have 187 times negative 38 plus 103 times 69 equaling 1. We'd like that to be equal to 5, so we're going to multiply through by 5, and we get 187 times negative 190 plus 103 times 345 equals 5. So we have x naught is 190, negative 190, and y naught equals 345. So our final solutions are of the form x equals negative 190 plus 103n, since d is 1, and y equals 345 minus 187n. Again, where n is any integer. And I hope that helps. Have a great day.